Hello, everybody in Taiwan and elsewhere. Today, we are very happy to be able to invite Dr. Paul Hartogh to give a talk on his instrument on the JUICE mission going to Jupiter. I should say that Paul is an old colleague of mine. I think we first met when he was a PhD student. Struggling with his work is not because he could not do it, because he has to do everything. He has to do everything for his advisor. Anyway, he received his master's degree and PhD degree from he worked at the Max Planck Institute for Aeronomy. At that time, it's now called Max Planck Institute for Solar System Research. But then his degree is from the in physics from the University of Göttingen. In 1985 and 1989, for PhD in 1989, and he started working as a staff member. We call it what do we call it? Scientific staff, scientific member. Yeah. Basically, we are the slave of the directors. That is the that's what he meant. But he is an expert on the microwave and fine infrared instrumentation. He's really good in microwave instrument. So for those of you who are interested in this, you should listen to talk carefully and ask him questions or write to him. In his career up to now, he's been the principal investigator of the Hartogh Solar System Observation Program on the water and related chemistry in the solar system. And currently he's the PI of the Submillimetre Wave Instrument called SWI on the JUICE mission to Jupiter, as we mentioned before. And of course, the SWI instrument is very important, for the JUICE mission. And he was a co-investigator on a number of very important missions and very important instruments. This including the very beginning on the millimeter wave atmospheric sounder (MAS) on Space Shuttle. That's when I first met him. He was working on that instrument, and subsequently he was the co-investigator of the microwave instrument on Rosetta, on the Rosetta orbiter called Miro. And he is involved in the terahertz instrument called GRIT on the Stratospheric Observatory for infrared astronomy, which is called SOVIA, which is a cooperation between Germany and NASA. He's very importantly also a principal investigator of the aerial mission looking for the atmosphere of a giant planet of the hot Jupiter of ESA. So he's really experienced in many of these instruments. Paul, so why don't you start your talk now?
Yeah, thanks a lot for the introduction, Wing. So I'm talking about the SWI on the Jupiter Icy Moons Explorer. I start with the science, and then I will talk a little bit about the technical challenges, also some PhD theses that have been involved, or PhD students that have been involved, or master students in developing the technology. So, so this is a sketch of the JUICE mission from ESA. You see the satellite in the background, and in the foreground you see Ganymede and the other Galilean moons. The interesting thing on the satellite is it has a really very big solar panel. It's nearly 100 square meters, because we are so far away from Earth, 5 astronomical units. So the solar constant there is about 50 watts. And in order to have enough power, you need really very big and very high efficient solar panels. So basically, we investigate Jupiter and the icy moons, or more precisely Galilean moons, Io, Europa, Ganymede, and Callisto. And with some kind of focus on Ganymede. And just for comparison with, for instance, the Earth moon in the upper left, here you see the size of the Jupiter moons. And you see that Titan is nearly as big as, for instance, Ganymede, which is the largest moon in the solar system. And here, for comparison, the diameter of Earth. Now, recently, Europa showed some kind of activity. Plumes have been discovered with the Hubble Space Telescope, but also with ground-based observation. And so the question is, so these were plumes of water. And here the artist in this case is Kurt Rutherford from Southwest Research in San Antonio. Imagine some kind of geysers you may have in Iceland, for instance. And so what people found out is that this kind of geysers are very big, actually much bigger than just shown on that artist view, but about 2,000 tons, 2,100 tons plus minus 658 tons were detected in this case with a ground-based instrument, basically Keck telescope on Hawaii. And they say that two former PhD students, it's Lucas Paganini and Geronimo Villanueva, both of them are now at NASA, the one at headquarters, the other at Goddard. And so our global survey at infrared wavelengths resulted in non-detection on 16 out of 17 days. The upper limits below the water abundance is inferred from previous estimate. On one day, 26th of April 2016, we measured 2,095 plus minus 658 tons of water at Europa's leading hemisphere. So obviously there's some activity. And yeah, we would expect also that Europa is the most likely moon where you have this kind of plumes because the thickness of the ice shell is believed to be only 10 kilometers. But there's also another atmosphere which is much thinner, which may have a total mass of 20 to 100 tons. Europa is an icy moon. It has an icy surface. It's rather bright. Has a relatively high albedo, so the ice is exposed to radiation, to high energetic particles, to sputtering, but also to solar light, causing sublimation. And so models believe that the water atmosphere around Europa may look like this. This is a paper of Christina Planacki. Now, anyway, this is a much thinner atmosphere, and I mentioned already total mass, maybe a factor of 100 less. But with SWI, we are rather near, and therefore we have not a sensitivity of 658 tons or so, but much smaller than 1 ton, maybe a few kilograms. We have here this topic of habitability, and here you see some table. What you need for habitability are basically these 4 points on the left side: liquid water, a stable environment, essential elements, SNOPS, CHONPS, and chemical energy. And for chemical energy, you need an ocean which may contain essential elements also to be connected to a silicate core. And all these 4 parameters are only available on Earth and on Europa. So let's go to Ganymede as an example, which has 5,200 kilometer diameter. And so you have an icy crust and then a saline ocean, and below you have an ice mantle that basically isolates the ocean from the rocky mantle. And then finally an iron core. Callisto, there's a very thin layer of liquid water, at least people believe it, but it is, let's say, less active or believed to be less active. And here you have an example for Europa where the ocean really is in connection with the silicate core. And you have all the requirements for habitability in principle there. So the mission, JUICE, they want to detect recently active surface areas and remains of plumes on the surface. I must say with SWI, of course, we want to measure the plumes directly if they are there. And so in the SWI team, there have been a number of PhD students modeling this kind of surface science, surface modeling. For instance, this case is Léa Bonfoy from Lesia in France, who worked on the icy moons of Saturn. Or we had a PhD student here, David Marshall, who was involved with the Rosetta mission and was modeling the ice properties of the comet 67P, the Rosetta comet. Here you see, for instance, 4 different temperatures and 4 different depths, 0 to 4 centimeters, according to the model, and the microwave instrument is able to sound to the different depths. And so we can constrain such kind of models. Recently also, so I'm a co-I also, maybe I forgot to write this, of Juno, the Juno mission, which is presently flying around Jupiter. And last year we had overflights of Ganymede and Europa, and in short time Io will be investigated. And so the microwave instrument MWR measured quite interesting results about the properties of the ice. Can't tell too much now, but I just say that 3 papers are submitted now. For modeling the surface parameters and how to get the physical parameters of the surface, we also did a number of models and also one experiment. One has actually nothing to do with SWI. It's a very low frequency instrument that operates at frequencies of maybe 200 kilohertz, that is using the Jupiter hectametric or decametric radiation as a source, and measures this radiation from the spacecraft and correlates it with the reflections from the surface and the subsurface. The advantage is you have very, very long wavelengths and can penetrate rather deeply into the ice, maybe up to 200 kilometers. So it should be possible with such an instrument to detect directly the ocean. But we also did submillimetre wave studies. It's another paper. So I did together with Jaroslav Ilyushin. Wing Ip probably still knows him. He was working under Hartogh in the 1990s at MPAE. And we developed a retrieval model for retrieving the parameter we measure with the submillimetre wave instrument on the surfaces of the icy moons. Here you see 2 pictures of Jupiter. So one is a Voyager picture from 1979 in the visible. The other one is in the infrared from Juno in 2019. At the South Pole, you see all these very small eddies. By the way, which is also a problem. If you model Jupiter, if you have a general circulation model, it's very difficult to model the general circulation because of the small eddies, because you have to model all the small eddies. They are important for energy and momentum transfer, which means in practice you need a very high resolution of the model, let's say 0.5 degrees in longitude and latitude. At the same time, Jupiter has a very high gravity. That means the scale heights of the atmospheres are low. So you need a supercomputer and you need a very effective parallelization in order to be able to really model the general circulation of Jupiter. In this respect, it's also interesting to model what happened with a great red spot. So if you compare, for instance, here it's a great red spot in 1890 and here it's in 2015. From the area it's less than half. And even if you compare 1995 to 2014, you see it's still shrinking. And the question is, how will it look like in 2032 when we are there in the Jupiter system? And is it still shrinking, and why is it shrinking? It's not clear. Interesting are also the Jupiter aurora. They are very powerful. And that was a picture here from the Hubble Space Telescope. The SWI people, they made also ground-based observation with ALMA. We try to measure winds with ALMA. ALMA has a high spatial resolution, and we measure to see winds in the pressure range of 0.1 millibar and 5 millibar. And so depending on where on the planet you point, you get quite different line shapes. So here you get a relatively broad line, which means you have contributions from the lower atmosphere where you have a high pressure broadening. And here at the pole, we only get emissions from higher atmosphere. This is all HCN. And from this kind of measurement, you can determine via Doppler shifts winds. And so we determined wind speeds of up to 1,300 kilometers per hour and an altitude of pressure altitude of 0.1 hectopascal. And this is quite different from what we expect from models, because the general circulation models, they expect that the highest wind speeds are at the equator, and then the wind speeds fall down towards the pole. So it's the opposite of what was expected. So Obviously, there's a physical process here which is not in the models, and this may have to do with the polar lights, some kind of coupling of the higher altitude ionosphere auroral jets with the stratosphere, which is maybe 200 kilometers, 300 kilometers lower. How this works exactly, it's not clear. There are several theories, and modelers are working on interpreting these results. Now, the JUICE mission consists not only of SWI, but of 10 instruments. And so here is an overview about the science that JUICE wants to do. For instance, I just mentioned the polar dynamic and chemistry, but also important for us are dynamic, winds, temperature, potential vorticity, bulk composition, isotope composition, etc. JUICE, the mission itself, has some high-level science teams, which are themes which are emergence of habitable worlds around gas giants and the Jupiter system as an archetype of gas giants. So, for instance, we want to learn more about the atmosphere of Jupiter, the Jupiter magnetosphere, and the satellite and ring systems. So it's a rather interdisciplinary approach. So I mentioned already 10 experiments here. In case of Ganymede, for instance, we have in situ remote sensing instruments, radio science, and radar. We have remote sensing instruments and radar laser altimeter for the surface, and so on. There are also instruments, radio science, that try to sound the extension, size, depth, and so on of the ocean and the iron core and the interior, basically, of Ganymede. So it's a relatively comprehensive approach of the JUICE mission. And here are the 10 experiments. So it's a radio science and laser altimeter, a camera system, a magnetometer, an infrared imaging spectrometer, a particle environment package, a subsurface radar operating at 9 megahertz, radio and plasma wave investigation, then the submillimetre wave heterodyne spectrometer, and the ultraviolet imaging spectrometer, last not least also VLBI experiment, PRIDE, which is using the spacecraft transponder. Here you can see the position of the different instruments on the satellite. Here is SWI. You can't see so much, but it's basically on the nadir platform. Here you have the high gain antenna. It's about 2.5 meters. And it operates in the K-band and in the X-band. In autumn 2005, ESA compiled a summary of the so-called Cosmic Vision program. So ESA always has programs for 25 years. And before it was called Horizon 2000. Now the next one is called Voyage 2050. But JUICE belongs to the Cosmic Vision program that has been published in fall 2005. And in December 2005, we had the first team building meeting for a proposal for a Jupiter mission. And so we had a proposal ready in 2007 called Laplace, after maybe 20 meetings in 2 years. And so when ESA asked for mission proposal, we submitted this Laplace proposal. Later on, the name of the mission was, first it was Europa-Jupiter mission, then Europa-Jupiter System mission. There the idea was to have a mission together with NASA, but that finally didn't work out because of the different funding schedules and time plans, time schedules. And so finally in 2012, it was decided to have a European-only mission, at least one satellite-only, called JUICE Jupiter Icy Moons Explorer. In 2013, we had a selection of scientific payload, and there were at the end 2 prime contractors. Finally, ADS won, and they're the prime contractor that built the satellite. Now, in about 2 weeks, the launch is planned of this mission, so 13th of April 2023, and arrival in the Jupiter system will be after basically 4 Earth and 1 Venus flyby or swing-bys, after 8 years in June 2031. And then the Ganymede orbit insertion will be 2034, and at December 2034 will be the end of the primary mission. If the spacecraft still has fuel, maybe there's an extension of the mission. Now, SWI is a radio telescope, but smaller and more expensive as we are used to. So for molecular line studies, radio telescope use heterodyne spectrometer. So what you see here in the background is APEX, the Atacama Pathfinder experiment in the Atacama Desert in Chile. And I spoke with Carl Menten from the Max Planck Institute for Radio Astronomy, who was heavily involved in developing this. And he estimated that the total cost of this telescope over the years was 25 million euros. And I can tell you for 25 million euros, you cannot build a radio telescope that flies to space, even if it's much smaller. So here we have a diameter of 12 meters of the main dish. SWI has a much smaller diameter, only 29 centimeters. So, but the commonality here is a heterodyne spectroscopy. So what is a Y heterodyne spectrometer? So I hope you know what heterodyne is. If not, I can later explain it. So because we have a very high spectral resolution, basically an arbitrary high, in our case, the requirement is 10 million. And heterodyne is a so-called coherent detection method, while other detection methods are usually uncoherent, where you have the spectrometer in front of the detector. Here, the detector is basically in front of the spectrometer with the heterodyne. But for instance, here in the neighbor institute on the other side of the street, in the Astrophysical Institute of the University of Göttingen, they are involved in CRIRIS+, which is an experiment on the VLT in Chile. And that has a resolution, CRIRIS+, of 100,000. Is a shell spectrometer, and that is the highest resolution you usually can get with non-coherent instruments. And on the other hand, this is not enough in order to resolve line shapes and to contain that, because these line shapes, they contain important information about the observed gas, for instance, density, speed of molecules, temperature. And so it's a fundamental to get the exact line shape of such a molecule. And here's an example from Rosetta Miro. You see a camera of the picture of the navigation camera of the Rosetta spacecraft, and you see the arrows show where the Miro instrument was pointing to. So you see here a dust jet with the estimated beam size and the measurement against the nucleus, here to cold space through the jet and here towards the nucleus. And in the one case, you get an emission spectrum because you measure against the cold space. So here you have basically zero. That's a cold space in Rayleigh jeans. So 2.7 Kelvin in Planck background radiation. And here you see the emission line, which has some very interesting features. And if you really want to learn with which speed and which composition the gas, in this case water vapor, is expanding, you really have to measure this line shape very precisely. Here on the right side, you see the measurement against the nucleus, and you see an absorption line because the nucleus is warmer than the gas, which expands. And if you would have a resolution of 100,000, that's the best you can get with non-coherent detection techniques, you would not resolve the line. You would have 1 pixel here from here to here, basically, or 1 pixel from here to here. And of course, you would smooth out everything and wouldn't get any information about this kinetic processes happening at the outgassing. We also did the same for the atmosphere of Ganymede. So Ganymede has a very thin atmosphere, surface-bound atmosphere. It's not 100% clear what causes this atmosphere. There are several theories. And you see, for instance, if you would work with a resolution of 1.9 times 10 to the 6, corresponding to a spectral resolution of 300 kilohertz, we would not be able to sample the line correctly. So the basically the black curve here is a line, and here we sample it with 300 kilohertz, and here we sample it with 100 kilohertz, corresponding to 5.6 times 10 to the 7, and that is the spectral resolution SWI, the SWI spectrometer has. That means with this resolution, we can sample basically this line shape correctly, and that is really required. Here is a sketch and overview about the instrument. So it's a heterodyne spectrometer. Here we have a actuator. We can move a telescope with a diameter of 29 centimeters in the one direction. So azimuth with plus minus 72 degrees and plus minus 4.3 degrees in elevation. The reason is that Usually, if we are in the Jupiter system, we always keep a distance of at least 15 Jupiter radii, corresponding to 1 million kilometers because of the radiation belts. So it's not good to fly in an area nearer to Jupiter than 15 Jupiter radii. And from this distance, 1 million kilometers, the apparent diameter of Jupiter is about 8 degrees. So basically, if we want to, if we fly in the equatorial plane, we can see the moons. Therefore, we have this relatively large, plus minus 70 degrees. But in elevation, the plus minus 4.3 degrees are enough because, you know, apparent diameter, as I said, is 8 degrees. And so we have 8.6 degrees. That should be enough. Then this radiation from the telescope is via beam splitter fed to two receivers. So here you have the mixers of the heterodyne receiver. Here you have the local oscillators, local oscillator signals, which are created by a relatively complex system. So we have tunable receivers. We can cover a relatively large frequency range. In the one case, in band 1 from 530 to 625 gigahertz. In the other case, from 1080 to 1275 gigahertz. And the intermediate frequency signal is then connected to the IF and USO distribution unit, and we have 4 spectrometers, 2 times 2 for each receiver, the so-called autocorrelation spectrometer, which is a wideband spectrometer with only 1024 channels, and then the chirp transform spectrometer, which has 10,000 channels with 100 kilohertz resolution. Now, a lot of technology which we are flying now didn't exist before we started this mission, and this technology was developed within this mission since 2005 or even earlier. So SWI consists of components and subunits that can be procured, even space qualified, like power supplies, data processing units, frequency distribution modules, ultra-stable oscillators, low noise amplifiers, and units not available on the market that have to be specially developed but are state-of-the-art. So, for instance, special data processing units, but the components are state-of-the-art. So, and then additionally, you need special technology development so that nothing exists on the market. For instance, maybe they exist, let's say, in some lab breadboards, and they are not available in space application, or they don't exist at all. Like in this case, for instance, the 1200 gigahertz Schottky receiver, the technology was just not there when we proposed it. Originally, we had American colleagues in the team, but they were not funded. And they also didn't have it, but they were confident that they could develop it during that time when we started. So 2005 to 8, the highest frequency receiver with Schottky diodes operated at 800 gigahertz, and the highest in Europe at about 600. And so when the Americans went out, we had to find a way how to develop this technology in Europe. We got funding from the European community, from national funding agencies and so on. And finally, we managed to develop a 1200 gigahertz receiver, by the way, within a PhD thesis. So most of these developments were indeed done by diploma, master, and PhD students. So, for instance, here, the 1200 gigahertz receiver was done by Diego Moro Melgar. He's now working in a company dealing with submillimeter technology in Germany. And so he started right away in 2013 to work on this technology with the help of several institutes in Paris and around in Spain. And yeah, this technology is now an integral part of SWI. Oh, myself, I started maybe nearly 40 years ago at the MPAE, where I also met Wing Ip. And my diploma thesis was to develop a chirp transform spectrometer. So I have, I could dig out some old photos, how a lab looked like in 1985. It's really amazing if you compare to today. And this was a baseline also for developing this spectrometer, which we are flying now at in JUICE, SWI. Here's an example of the first application of the spectrometer that was in Effelsberg. So here is a 50 years anniversary stamp of the 100-meter radio telescope in Effelsberg in Germany, in the Eifel Mountains. And so on the upper panel, you see the big spectrometer they had. They had 10 kilowatts, fully digital. And so here was my spectrometer, which was also relatively big, but only 1 kilowatt, 30 kilograms. And I think the quality of the spectrum of my spectrometer was substantially better than what they had during that time. So what really progress. Yeah, and later in 89, I used this also for measuring atmospheric lines and made my PhD thesis on that. And then a spin-off of the PhD thesis was the chirp transform spectrometer for Rosetta Miro. Here we managed to reduce the mass from, what did we have here, 30 kilogram to 2.3 kilogram, and the power from 1 kilowatt to 15 watt, thanks to the availability of field programmable gate arrays. They came out in the basically in the second half of the 1980s. Also, the performance here is better, 4.5 times the bandwidth, and 4 times the channels. Then we had a number of PhD theses, for instance, on the chirp transform spectrometer, or also on other technologies. I just show here 3 examples. So that is the guys who measured the plumes at Europa. I showed before, Villanueva and Paganini. They worked on the chirp transform spectrometer on signal processing and on accuracy, how we can increase accuracy. And yeah, then we had another PhD student from China who worked on the key component of this, one of the key components of this chirp transform spectrometer, surface acoustic wave filters, so-called reflective array compressors, fabricated using E-beam lithography, together here with the so-called with the Physikalisch-Technische Bundesanstalt in Germany, the Metrology Institute here in Germany. They had very nice equipment so that you can we could develop this kind of device. And here's an example of such a device. Basically, here's a substrate. It's a black substrate of lithium niobate. Here you have grooves, so about 20,000 grooves. So therefore, in the light, they show this rainbow color. And so here's some test setup where you just put in this piece of lithium niobate with a structure on it and measure the performance. Here's a typical example of the size of each group, 40 nanometers deep and 200 here on the bottom, 295 nanometers wide, and at the top 328. And everything is very, very important that all this 20,000 grooves all have a very dedicated shape and a dedicated depth. So each group has different parameters. And that was really a big effort. And finally, we used such a device also for SWI. Here's the engineering model. But you have to qualify this. And so I was told maybe it's interesting to speak also a little bit of how to qualify this kind of component. So basically, this component was just developed from the scratch, out of nothing, just a lithium niobate substrate with some theory how to build this kind of devices and with nice equipment. And so here it's glued into a COVA case. COVA is used because it's a metal that has the same thermal expansion coefficient than the substrate, the lithium niobate, because in space you may have very large temperature differences. So the package should have the same expansion coefficient than the substrate. Otherwise, you get trouble. And so that has to be qualified because it's a completely new component. And here I just want to show the qualification plan for the surface acoustic wave filter. And what I show here is just it took almost 6 years until all the parameters we had to qualify were really clear and were really ready. So we were ready for the qualification. And here's such a qualification plan. You have to do the lot acceptance test. Lot means you start with a number of such filters, in this case 40, and then you have to go through a number of processes and procedures, the so-called process monitoring, review, internal visual inspection, adhesion of metallization to substrate, wire bond strength, sealing of the case, dimension check, weight, and serialization, high temperature, bake out, temperature cycling, mechanical shock, PI&D tests, so whether there are dust particles, room temperature, electrical measurements, burn-in, high, room, low, drift temperature calculations, and electrical measurements, check for lot failure, and then the so-called radiographic inspection, and finally the seal. And then from 13 samples out of the 40, you do mechanical testing, lifetime testing, radiation testing, and go through all these parameters. And so each single task has its own document at the end, and it's done according to some specifications. For instance, internal visual inspection has to be done according to the European space standards, ESCC 204-3502. And then you have here the adhesion materialization according to ECSS, so both exist, ESCC and ECSS. Or for instance, the wire bond strength destructive done according to military standard 883-2011. And so, for instance, this monitoring review you do for all the samples, but the destructive test only for 2, because you still want to use some, and so on. Now, here's another example for the temperature cycling. So each parameter at the end has its own document, and so you got I think we got about 600 pages of documentation for the qualification. I just show some examples here. Here, for instance, the bond strength test. So the requirement was a pass specification 2.5 grams. So basically, they bond a bond wire to a 100 nanometer thick aluminum layer, and then have little weights and see under which weight basically the bond is destructed. And so here we are everywhere. The weakest was here 6.8, but the specification was 2.5, so we passed. Then we have developed 2 ASICs, application-specific integrated circuits, and this ASIC development, so the SAW filter development, by the way, started actually in 2005. And here the ASIC development also started 2005, and we first did a detailed functional description and modeling, which took 3 years. Then we were looking for a suitable space qualification, space-qualified process. We also had a TSMC process in mind, but finally we decided to use a European process in 2013 for the so-called preprocessor. It's a radiation-hard 65 nanometer CMOS ST microelectronics, because this was subsidized. So the space qualification, radiation qualification was subsidized by ESA. And then for the trap generator, that's the other ASIC, we used a process which was developed in Germany by an institute called Institute for Semiconductor Physics in Frankfurt, or near to the Polish border. And here the qualification, the documentation, specification, and documentation altogether is more than 2,000 pages. That is how such an ASIC looked like. So you see the chip in the middle, you see a so-called interposer, which is this PCB around, which is basically needed to connect this chip to the pins of the package. The package is roughly about 1 centimeter times 1 centimeter. And here it's important, for instance, because this chip is working with a clock frequency of 16 gigahertz. So there are some radio frequency lines. So this interposer, this PCB, has to be designed in a way that it has transmission lines, and it can basically transfer radio frequency signals up to 16 gigahertz. So therefore, this bond wires are all extremely short, so fractions of a millimeter. Here we have the preprocessor. The chip is much smaller. It's 2 times 2 square millimeters, and so therefore the interposer has to be bigger because the package is the same. And so here is from the pre-cap inspection some photos how the chips are bonded to this interposer and how the interposer is bonded to the pins of the package. And here's just one example. One of the many qualification tests we had to do is a single event effect test. And we went to Belgium. There was an accelerator that could produce the particle energy spectrum we expect in the Jupiter environment. And basically, you can see we needed a truck to transport the test equipment, altogether maybe a ton of test equipment. And here you see the accelerator in Leuven in Belgium. And here you see the device under test is on this little PCB. And here you see the accelerator closed. And finally, here is the chip. That's the chip you just saw in the package, which is a device under test. And maybe the chip has a weight of 0.2 grams. And you need 1 ton of test equipment in order to test it. Now here you see the chips already with some additional shielding in the PCB of the church transform spectrometer. And yeah, then we come to the telescope and receiver unit. Here it's also interesting that the material we had to use is not aluminum, it's Albimet, it's a AN162. It's a special alloy which has to a certain extent features than stainless steel, but a density of only 2. And so you can mill it very, very thin in order to save mass. And yeah, here you see basically the mechanism for the long track, so the azimuth, and here a cross track for the elevation. And this is a receiver, the submillimeter wave receiver. I don't have too much time to explain details. Here's electronic units with the spectrometers, with the DPU, with the power supplies. Here are some more photos from our lab. Here we have the flight unit. Here we have the structural model. From outside, they look the same. And so here we have in our shaker the photos from the vibration test. Here from our anechoic chamber, the so-called EMC test. And so here both the flight model connected together, and finally connected here on the satellite. Here you see the radiator for cooling, and here you see the telescope and receiver unit. This electronic unit is inside in a vault, which has a few centimeters of aluminum for shielding against harsh radiation in the Jupiter system. Quickly about the near field test. So the problem is, if you want to get the telescope pattern, so the antenna pattern, so to speak, in the far field, you would need a chamber with 700-meter length, because the far field of this telescope is in a distance larger than 700 meters. And of course, there's no vacuum chamber that is so large. And if you are in the submillimeter wave range, you cannot measure in the atmosphere, because the atmosphere is absorbing the radiation. So the alternative is you make a near field measurement, where you measure amplitude and phase instead of power in the far field, amplitude and phase in the near field. And there was a new chamber developed at ESTEC, which has 3 meters diameter, is 4 meters long, the so-called Lorentz chamber, Lorentz facility. And SWI was the first experiment that was measured in this chamber. Here you see it. So it's a rather big chamber. Here's SWI. And the whole shroud here has some kind of anechoic material. And yeah, what you see here is the amplitude and the phase in the near field of the antenna. And that's the calculated far field pattern. And here we have, that was 600, here's 1200 gigahertz. Here you see the 1200 gigahertz beam. And finally, we measure the copolarization here, in one case a cross-polarization. And this shows you how large the beams are and how good the two frequencies are aligned. Now, a few words about the science goals of SWI especially. So we want to measure the structure, dynamic, and composition of the stratosphere of Jupiter, and the coupling mechanism between the lower and the upper atmosphere, the dynamic and composition of the atmospheres or thin exospheres of the Galilean moons, for instance, for cryovolcanic activity. We're also interested in the auto-to-para ratio of water to learn something about where the water was formed. We would like to know about the isotopic ratio to learn something about the origins of the moons, and finally about the thermophysical properties of the surface. So the Jupiter stratosphere is shown here. It's basically between 50 and 320 kilometers above the 1 bar layer, and it's rather unsampled. Here's an example of our general circulation model. That was a PhD thesis from 2014. And you see we expect relatively low winds, the wind speeds at the poles, in contrast to what the ALMA measurement showed. Here is still from this 2014 model, which is obviously wrong, or at least doesn't include all the physics. A way how to constrain the model is to measure spectral lines. In this case, it's methane line at 1256 gigahertz. And from this line, we will be able to retrieve vertical profile and of temperature and of winds. Here is a number of isotopes we can measure: H217O, HDO, H218O, etc. of C34S as an example, or HC15N and HC13N, etc. Then, okay, the question is about the D/H ratio. So what is the D/H ratio we can expect in the atmosphere of Jupiter and also in the thin atmospheres of the satellites, the Galilean satellites. And here is just to show, it's one sketch to show that there may be a change of d/h with heliocentric distance. So the idea is that in the early disk, when the solar system forms, you have rather high temperatures in the inner solar system, and 99.99% of the material is hydrogen gas, H2. And you may have very highly deuterium-enriched water ice, which is then mixed within the disk. And once it comes to the inner disk, where the temperatures are very high, it may be equilibrated with the deuterium of the H2, because there's 10,000 times more H2. So it will get the d/h ratio. The water will get the d/h ratio of H2. But when you come further out, it gets colder, and you get some mixture of this equilibrated water with this highly enriched, deuterium-enriched water. And so therefore, the further you go out, the higher the d/h should be. Yes, and this d/h ratio was measured in the number of comets, Oort cloud comets and Jupiter family comets. You have a scatter here between 2 or 3 times the Earth d/h ratio, the Vienna standard mean ocean water. And we have a number of Jupiter family comets where we get, except 67P, that's some outlier, we get d/h ratios like in the Earth's oceans. The d/h ratio here of Jupiter, Saturn, Uranus, and Neptune, much lower, but that is d/h not in water, it's d/h in hydrogen, so HD. And we hope that with SWI, we will be able to measure this d/h ratio of Jupiter in water for the first time. The atmospheres of the satellites are very thin, so therefore the spectra you get are so-called non-LTE spectra, so you cannot assume a Maxwellian distribution of excitation state of the molecules, and you have to develop specific non-LTE models, and this is an example, and you see this self-absorption and this very specific line shapes you usually don't see in planets. You only see in moons. Also, you don't see them in comets, because in comets the gas is moving, while in the moons it's still somewhat gravitationally bound to the surface. Also, the atmosphere is really thin. And so we also developed some models here. This is an example of Eva Wierström from Chalmers. She has used a 3D model, which was developed by Brinch, who is now at the research group of genomic epidemiology, National Food Institute. So he had, before he was an astronomer, developed a 3D non-LTE radio transfer model for the interstellar medium, which was in this case applied to Ganymede. I mentioned already that we are interested in measuring the plumes, and so here we have some example of gases we can see, H2O and the isotopes H2O to O2, methanol, CO, H2CO, etc., and with some sensitivities. So that are the column densities, something in the range of 10 to 14 to 10 to 15 per square meter, which is nanograms or picograms of the molecules, very little. So we are very sensitive here. And altogether, in the tuning ranges, we have, I think, 85 molecules. And so if we investigate a plume, and if we know what molecule to expect, we could tune to this molecule and try to find it. It may be not possible to measure all molecules one after another, because the integration time for that may not be sufficient. So you can usually only see 1, 2, or 3 molecules at the same time. So you have to decide what to look for. For instance, whatever, H2S. So maybe we look for molecules that indicate habitability, like metabolic products of bacteria, etc. But we are at the moment discussing what kinds of molecules are most promising to observe. Yeah, and here we have a little movie. I hope it works from the launch, and showing the swing bys. So hopefully that happens, that all functions and works in 2 weeks from now. So another Earth flyby. Then there was originally a Mars flyby. So this is a little bit out of date, because there will be no Mars flyby, unfortunately. another Earth flyby, and then finally the arrival in the Jupiter system. In 2031. Then last not least, a few words. We will also have a Venus flyby. You could just see it. I didn't mention it. And maybe you have heard that in 21 there was it was claimed that phosphine gas was detected in the cloud decks of Venus. And pH3 may originate from unknown photochemistry or geochemistry, but there is some kind of biological production on Earth. So it was discussed whether there's life in the clouds of Venus that produce phosphine. So unfortunately, I believe that we cannot really believe that this measurement was real. And so then I was member of a rebuttal paper saying that there's no evidence of phosphine in the atmosphere of Venus from an independent analysis. So we analyzed the data. Then later on, we had also Sophia great time to observe phosphine. We didn't see anything. The data was DDT time, so director's time, so it was public. And then the group here, they analyzed the data and they found phosphine. So that is still under debate. But with SWI, we will be able, so at the moment, the sensitivity we have is something like 5 ppb upper limit of phosphine. But with SWI, as this simulations show, we will be able to measure, to get 3 sigma upper limits of 15 parts per trillion. So we'll be almost a factor of 300 more sensitive than what we had now. And so hopefully then we can clarify whether there's phosphine or not. Last not least, if you are interested in learning more about the JUICE mission, there is ESA TV, or you can also find it in YouTube if you type in the making of JUICE. There are, meanwhile, I think 11 episodes. The latest one is 10.2, and it shows basically all details about the satellite, about the mission itself, about the science, about the different instruments. And so the people are interviewed who are building the instruments, etc. So it's quite interesting to watch it in case you should be interested in JUICE. Thank you very much for your attention.
Yeah, thank you so much, Paul, for this very comprehensive talk on the SWI instrument. I think that we have a number of microwave experts, either theoreticians or observers in the audience. Maybe they would like to have some questions to Paul. If you have questions, you could raise your hand or just turn on your mic and ask. Or you could also write, on the chat box for Paul to read. Anyone? Maybe I ask Paul first. Of course, I'm very interested to know whether Juno will have a couple of Europa encounters. Is that right?
Yeah, had it already. Yeah.
What have they found? Have they found something very interesting, or you don't want to tell us?
Yeah. So what we found. So I'm only in the MWR. So I'm basically also in the science team, but I do not have time to participate in the findings of the other instruments because I'm still busy with SWI. But at MWR, so the microwave radiometer, we found quite large differences in the microwave brightness. So this instrument has 6 channels starting at 600 megahertz up to 22 gigahertz, which is believed that the different wavelengths penetrate into different depth of the surfaces. And so what I can say is that Europa and Ganymede look quite different. So that means the first centimeters or meters of the ices seem to have quite different compositions. But more details, I think I cannot say before the papers are published.
Well, of course, I think that one can imagine that because Europa basically the ice cell is very fresh, right? The Ganymede is still part of it, if not all of it. The surface is quite old.
Yeah. That you clearly see in this MWR data.
But no immediate discovery of water plumes and things like that.
No, MWI is not cannot discover water plumes. I think that's for that you have to go into the submillimeter or at least millimeter wave, because the cross sections of the lines are just too small. So the lines are too weak in the range where Juno measures. Juno is MWI is mainly designed for instance, measuring the deep atmosphere of Jupiter, and yeah, maybe just the surfaces of the Galilean moons, but not let's say to measure molecular lines in the regime of 1 bar or below.
I mean, the instrument on Juno measured down to about 100 bar.
Yeah.
And then how about yours?
Maybe 0.5 to 1 bar.
Oh,
we measure, let's say, 1 bar to, in the best case, 1 microbar.
Yeah. But why is that? Because now the new finding says that from Juno, that the ammonia, there's a very, very deep convection down to 100 bar at least level.
The main reason why we cannot, with SWI, measure so deep is the so-called collision-induced absorption of helium and hydrogen. That means you have two molecules that usually do not have an electrical dipole moment, except for the very short moment of collision. And so these collisions, they take maybe 10 to the minus 12 seconds or something like that, in that range. And for a very short moment, you have a dipole moment, and you get some very broad absorption, which basically covers the range of maybe starting at 50 gigahertz, 20 gigahertz up to the infrared, maybe 10 terahertz or so. Therefore, we cannot look below this kind of cloud created by this absorption through this collisions between helium and hydrogen. It's similar on Venus with the CO2.
Okay. Now, can I call some name in case they have questions? Wendy, do you have a question to Paul?
Yes. Hi, Paul. This is Wendy.
Hi, nice to meet you again.
Yeah, nice to meet you too. So, okay, let me see. You mentioned the ice composition in the shallow surface could be very different from Europa and the Ganymede. So I'm just wondering, so would you expect the Ganymede or Callisto still have some level of plume activity?
Yeah, Europa, I think Europa we know, and I think that we do not exclude any activity with SWI. So basically, once we enter the Jupiter orbit, equatorial orbit, we will every day for about 1 hour scan over the 4 moons, Io, Europa, Ganymede, and Callisto, and look, for instance, for water, because water is most easily to be measured. And there have been several plumes detected on Europa and also Ganymede recently.
Oh.
And actually, we have Herschel measurements also where we can see some activity there. Not published yet, but it's going to be published soon. So, so there's, I'm quite sure there's activity, maybe even also some activity on Callisto, but it's not clear what is causing this. There may be different physical processes.
Oh, okay. Thank you.
All right. Maybe I can see somebody else. 关老师。
Okay. Paul, let me turn on my camera. Yeah. Can you see that? Okay.
Yes. Yes.
Yeah. Hi. Yeah. I'm sorry. I joined late. I got stuck by other thing. I heard you say the phosphine things. When will that happen? When you fly by to Venus?
Yes, in 25 we have a Venus flyby.
Oh, in 2 years.
Yeah.
Wow. So okay. Did you say also? Did you say you have this Herschel data of the activity on Ganymede and the Callisto? I mean, the plume activity you detected?
Yeah, so we had some guaranteed time for that, and tried several times, and then we saw something, then we didn't see something, and then we realized. So it's a complicated stuff. We saw something in the second side lobe. It turned out it was Jupiter and things like that. But we are also quite sure that there is some activity on the moons themselves. So Ganymede and Callisto. Yeah.
Did you try Europa? No.
Yeah. We tried to get open time, but unfortunately, the referee said no. There will be nothing. There are no atmospheres. Forget about it. So we don't have. Of course, we wanted to do all the 4 satellites, and we had a proposal for 50 hours, and it was never accepted. And of course, now it's a hot topic, right?
Yeah.
And now you cannot measure it. You have to wait for Herschel. I don't know if you can measure water with ALMA, but I don't. Maybe 183.
Okay. Yeah. Okay. Thanks.
Okay.
Paul, once he told me that he built this instrument on Herschel, right? And asked him how much the instrument cost. Can you tell us how much it cost? If you still remember?
Herschel?
Yes.
I just know Hi-Fi. I was involved in Hi-Fi. There were 3 instruments, Pax, Spire, and Hi-Fi. And Hi-Fi was altogether something like 300 million euros.
Only 300 million?
Yeah, 300 million euros. Yeah.
300 million euro. Okay.
Yeah, I think there were more than 2,000 people involved in building this instrument.
Okay. That's a very cheap instrument. Okay. Any other questions from the audience? If not, I will let Paul go, because I think everybody's ready for the long vacation we have for next few days. All right, Paul, thank you so much. I think we'll hear from you. I will hear from you. Once the launch is successful, the Jules will ask you to give talks again.
Yes, hopefully it's successful. Yeah.
Right. Okay. Great. Enjoy your vacation too. Yeah.
Thank you.
Bye-bye.
Bye-bye.
Bye-bye.